Good afternoon, dear colleagues, one more time. My name is Irina Sarkisyan, and I'm the head of Nuclear Education Transfer Project Office at Rosatom Technical Academy. And today we hold a webinar called Small Modular Reactors, Flexible and Affordable Power Generation. So dear listeners, if you will have any questions to our speakers, I suggest you to ask them right after the presentation. I think it will be easier to everyone. So first of all, I would like to thank to our colleagues, the organizers of our meeting, the Egyptian-Russian University and the ambassadors of Russian nuclear education. And I think we can start, and I would love to give the opportunity to say welcome words to Mr. Moustafa Saleh, Associate Professor of the Faculty of Engineering and Mechatronics and Robotics of the Egyptian-Russian University and former manager of the Research Nuclear Reactor of the Egyptian Atomic Energy Authority.
Thank you very much. Thank you.
Yeah.
The voice is clear?
Yeah, I can hear you very well.
Thank you. Good afternoon, everyone. On behalf of Head of Egyptian-Russian University and all the other esteemed organizing institutions, I would like to welcome all those present here for joining us in the first event jointly organized by the Egyptian-Russian University, along with International Atomic Energy Agency and the ambassadors of Russian nuclear education powered by Rosatom. It's a great honor for me to be able to attend such a valuable event today. In fact, such events will be an opportunity for us to learn from each other by sharing our valued knowledge, ideas, and experience. The event topic is the small modular reactors. In fact, these reactors have been attracting great interest recently as a potential way to meet the increasing global energy demand while reducing greenhouse gases emission at the same time. Compared with traditional nuclear power stations, small modular reactors offer various advantages, including less capital cost, improved safety features, and increased flexibility in terms of location and application. Smaller modular reactors are viewed as promising technology that can offer a reliable, sustainable, safe source of clean nuclear energy in view of the growing worries over climate changes. Unfortunately, the study in nuclear power stations in engineering department in ERU was suspended last year for procedural reasons. I hope to resume the studying in the department soon. Now, let me mention a little bit about the cooperation between ERU and the Russian side, especially Rosatom and Tomsk in the last 5 years. The Egyptian-Russian University was founded according to the Presidential Declaration in 2006, based on the mutual cultural protocol between Egypt and the Russian Federation. ERU has been established with the support of 7 Russian institutions. I am going quickly to review the aspects of this cooperation. The cooperation talks between ERU and Tomsk started in March 2015 with a delegation visit from Tomsk to the ERU headquarters. In 2016, a delegation from Rosatom visited ERU headquarters to discuss the various aspects of cooperation. The educational system of nuclear power station engineering program was as follows. The study duration was 5 years and a half. According to the signed protocol, the students of nuclear power station engineering program implemented the first 3 years in ERU. They studied the main subjects, like, for example, atomic and nuclear physics, electronics, electrical engineering, thermodynamics, and heat transfer, and so on. Then they traveled to Russia, Tomsk Polytechnic University, to spend the last 5 semesters, 2 years and a half, to study reactor engineering, turbo machinery, neutronics, reactor kinetics, shielding, and nuclear power stations, etc. At the end, graduates get double degree certificate from ERU and Tomsk. 48 of our students who studied at Tomsk have been graduated. It's worth mentioning that 20 of them had received full scholarship from Rosatom, and the 22 students have received partial scholarship. At the end, ERU is grateful for the cooperation with Russian Nuclear Education Ambassadors, International Atomic Energy Agency, and Rosatom. ERU is looking forward for more fruitful cooperation with you. Once again, on behalf of head of Egyptian Russian University and the other organizing bodies, I deeply appreciate your participation, and I hope you enjoy this special event. Thank you for your attention.
Thank you very much, Mr. Moustafa Saleh, for your kind words and for all information about cooperation between universities. And we will come back to your presentation a bit later. So, dear colleagues, I guess we can move on. And today the topic of our meeting is small modular reactors, flexible and affordable power generation, as far as you remember. And the concept of small modular reactors, or SMR, and their application in power generation have been the subject of many discussions by scientists, governments, officials, and experts in the field of nuclear energy from all over the world for last years. In this regard, I would like to introduce Mr. Vladimir Artisuik, Senior Nuclear Expert, SMR and Fusion from International Atomic Energy Agency. Mr. Artisuik, could you tell us more details about this type of reactors, please?
Yeah, thank you, Irina. And I would like to share my presentation with you. So I share screen. So share.
I'm in the host. Yeah.
Can you see this?
Not yet. Yes. Yeah.
You can.
Yes, we can.
So my pleasure to work with you today and give you a presentation about small modular reactors and platform for small modular reactors, and this is activity in the agency. So I'm starting with the political level, and as you can see here, this slide shows the results of the statement of the Director General of the IAEA in his opening speech to the 67th session of the IAEA General Conference. It was last September. I would like to stress several lines here and draw your attention to what is going on in the agency. So you see the first statement: nuclear power capacity will need to grow significantly in the world to meet its climate goals. That's first statement. Second, part of that growth could come from small modular reactors. So small modular reactors are expected to play a significant role. And the IAEA platform on SMRs and their applications provides member states with enhanced agency support on this important emerging technology, whose modular design allows for a more gradual scaling up of power capacity, making SMRs especially relevant to developing countries. So these are the key words. Climate goals, small modular reactors, and developing countries. So the outlines of my presentation will deal with the interest in SMRs and overview of the development. I touch on several SMR designs and their challenges, and finish with the activity of the agency on that point. So my first slide is a nuclear in a climate context. What's important to get from this slide is, please have a look at the bottom right portion of the slide. Here you can see the emission of CO2 from various electricity producing technology. And you can see that nuclear is the lowest one. So the footprint in terms of CO2 emission from nuclear even less than from offshore and onshore wind and hydropower and solar. And by the way, what is important from this graph? This graph is from the data published by International Platform for Climate Change. And this International Platform for Climate Change, that is United Nations organization, and that is not promoted by nuclear or other technological organization. It is purely environmentalist organization. So that is conclusion of environmentalists, that fusion is the best from the viewpoint of CO2 emission, the lowest one. Also, please pay attention to the global greenhouse gas emission by economic sector. You can see that electricity and heat production, that is just 22%. But you see industry and transportation and even building, they produce a rather appreciable portion of CO2 emission. Especially pay attention to the industry and transport, 35%. Not electricity production, but cargo ships that moving through the seas, cars, manufacturing of steel, manufacturing of cement, producing cement, they also have a rather appreciable CO2 footprints. That's why to reduce dramatically the CO2 emission, the Paris Agreement was signed in 2015, and the main idea of this agreement, Paris Agreement, is to achieve balance between anthropogenic emissions by sources and removals by sinks in the second half of the century. Pay attention, second half of the century. So you can easily after that recognize this slide. Please pay attention to the bottom of the slide. We are now in 2024. Paris Agreement, that is zero emission 2050, and we need a technology to drastically reduce CO2 emissions. And small modular reactors, since they are small and provide the possibility of modularity and provides the possibility to be produced, mass produced in the factories, they are one of the solutions. And in order to get these advantages of these reactors, I mean mass production, first of a kind SMR should appear about 2030. So we have only 6 years to demonstrate that nuclear power technology, especially with the small modular option, has a chance to drastically reduce the CO2 emission and solve the problem of climate change globally. So that is the point, very important. So the nuclear in the context of newcomer countries, since especially for newcomer countries, the small modular reactors are of main interest. Now we have 20C 27 so-called newcomer countries that are expected to get the benefits from nuclear power. So, and that is dynamic of SMR designs globally. I would like to stress that in the agency, we have special publications on SMR technology development. And this publication appears once in 2 years. And in 2012, there were only 32 designs globally considered in SMR's domain. And you see that growth is dramatical. And 2022, just 2 years ago, it were 83 designs included in the collection of the potential designs published by the agency. So 32, and within 10 years, 83. That is also provides the illustrative effect how interesting this theme is for developers also. 83 designs. And if we look through the number of the countries that provides this kind of possibility for new designs, you can see that not only so-called well-developed nuclear countries like United States, Russia, China, Canada, Japan, UK, but also South Africa, Czech Republic, Denmark, Netherlands, Sweden, they also provide these designs for the future market. So the number of the developers, the number of vendors are also drastically increased. And the number of SMR designs is, if we can categorize them, so you see only 38 of them belong to water-cooled reactors, to common and well-developed, well-matured technology. But 45, they belong to advanced reactor, high-temperature gas-cooled reactor, molten salt reactor, lead fast reactors and sodium fast reactors. But again, pay your attention that majority is high temperature gas cooled reactors. Later on, I will show you why so much attention is given to high temperature gas cooled reactors. Categorization of SMR technology in the agency, which you used to be along with, they are land-based water-cooled reactor, marine-based water-cooled reactor, liquid metal-cooled fast neutron reactor, molten salt reactor, high-temperature gas-cooled reactor mentioned above, and micro-reactors. New type of the reactors are coming to us for consideration. And this slide shows you then all the mosaic, all the palette of the designs considered globally. But you can see that some of them belong to pre-conceptual or just conceptual design. There are several of them in the domain of basic and detailed design. Detailed design is the most mature design. 3 of them under construction, Cairo in Argentina, ACP 100 in China, Brest 300 in Russian Federation, and 2 of them are in operation. Floating nuclear power plant in Russia and high temperature reactor in China. So you see 2 in operation, 3 under construction, and many designs are coming as a potential designs at various stages of the development. Let me show you just examples of the PWR types, small modular reactors, that is pressurized water reactor type. There are several of them on this slide. Cairo ACP 100 from China, SMART from Korea, Voyager from the United States, and Rhythm 200 from Russian Federation. What's important to look at is enrichment. Please pay attention to the enrichment. For Cairo, that is about 3%. For ACP 100, for SMART, for Voyager, it is about 5%, but for Russian type, that is about 20% uranium enrichment. So you see the trend is to increase enrichment. Here is for non-electric application. For non-electric application, we mostly need high temperature, that is for industrial use, for seawater desalination, for methanol production, for petroleum refining, etc., etc. And that is an industry. And for industry, we need to provide high temperature. And only very high temperature reactors, or gas-cooled reactors and molten salt reactors are very much attractive for that option. And just to remind you that industry and transportation provides CO2 emission about 35%. So that is exactly the task and option for high temperature and molten salt reactors. And if we have a look at the projects in the domain of high temperature gas-cooled reactors, you can see that enrichment is rather high, about 20%. So that is just one of the most important findings through reviewing all the design. The majority of the designs are looking for highly enriched uranium, and that is a special uranium. You see, there is special title for this uranium, high assay low enriched uranium, high level. That is fuel with enrichment between 5 and 20%. And if we have a look how many designs rely upon high level, that is more than 50% of the design considered in the IAEA collections. And demands for a high level will be drastically increased with the time. You can see here the slide showing high level demand projection in the United States and Canada. You can see exponential growth. And also the same situation is understood in the European countries. Currently, by the way, the only United States of America and Russia, they can provide high level at a commercial stage. But capacity is not so high, so that's why United States of America, they adopted special program to produce high level, and also United Kingdom and France. So, but because of the lack of high level uranium, some of the projects now postponed. So another very interesting feature associated with the small modular reactors. In 2021, there was a publication appeared in the brochure of Electric Power Research Institute, Rethinking Deployment Scenarios for Advanced Reactors. So that's published in 2021. The main idea of this publication is that serial manufacture both SMR and ships is considered as a viable option to rapidly change the landscape of carbon emission from heavy-duty transport, as well as for hydrogen production and power sources for electricity and water desalination. So floating nuclear power plants coming at the stage as a very, very attractive option. So, and 2 years later, in 2023, last year, it was by initiative of Director General of the agency, we conducted special symposium on deployment of floating nuclear power plants. And they finalized and emphasized that shipyards worldwide have a proven records of serial production, and cross-industrial cooperation is important for integration of nuclear quality and standards into existing shipyards model. And this year, in April, special new organization was established, Nuclear Energy Maritime Organization, with the mission to help national and international regulators to create future-oriented standards for floating nuclear power. And this year, Director General of the agency had a special meeting with the consulting firm Lloyd Register, located in the United Kingdom, which is specifically pursuing nuclear maritime transport. So you see several new trends are coming. And in the agency, we have a SMR platform created in 2021 that serves as a focal point for IAEA activities in the field of small modular reactors. Here, very important point in this slide. Please pay your attention to the email address, smrplatform.iea.org. If we receive through this mail some requests from the countries, not from the individual persons, from the countries, from the stakeholders like universities, like industrial enterprises. If they have any request to us, we can mobilize resources in the agency to respond to this country, to help them to understand better what is going on with the small modular reactors development globally. You can see what kind of activity this platform is producing now. Main activities last year. We organized special expert mission on nuclear desalination for Jordan. We reviewed the conceptual design of research high temperature gas cooled reactors for Poland. We made interregional events on technology development and generic uses requirements for SMRs in China, and also organized symposium on the deployment of floating nuclear power plants, which I mentioned above. More than 150 participants from 44 member states participated in this meeting. And what's important, you see, coming in 2024, International Conference on Small Modular Reactors and their Application, coming October. And I'm sure that several presentations from Egypt were selected to be presented at this first-of-a-kind meeting, by the way. So, summary, I will give you that information that is very much growing interest in SMR globally. And the various SMR design under development at various stages globally. And there are some challenges that should be addressed in a timely manner. As I mentioned, high-level uranium is needed and not enough capacity for producing this uranium are on the stage. And IAEA SMR platform provides coordinated support in the areas of technology development and demonstration, legal frameworks, high standards of safety, security, and safeguards. And with this, I would like to thank you for giving me the chance to present the activity of the agency for Russian Egyptian University in Egypt. Thank you.
Thank you very much, Artisuik. I want to take an opportunity and my role as a moderator. And first of all, I want to say thanks one more time for a very interesting presentation, but I want to ask the question.
Please.
So the first question, I think there will be more questions. I'm a person who shares the values of sustainable development goals, and as a member of community of women in nuclear industry, I can't resist to ask, how does the introduction of SMR and low power nuclear power plants contribute to achieving the goals of sustainable development goals of the country's energy sector? As far as I remember, it's 7 Sustainable Development Goals, clean and cheap energy.
No, as I mentioned, it was one of my slides, particular slides, that Sustainable Development Goals is about clean energy production. We have, you see, connection and links between these Sustainable Development Goal and Paris Agreement. They closely link. Sustainable Development Goals and the Paris Agreement we appeared the same year, 2015, by the way. So that's why they linked. And you remember the target of Paris Agreement, it means the Sustainable Development Goal for electricity production, 0 CO2 emission by 2050. So we need to establish new power source for electricity production, new power source for industrial application, new with the low CO2. And only nuclear is the lowest one. We need more nuclear, but how to produce more nuclear with the current technology? So we have to change paradigm. We have to produce nuclear reactors in a manner like now our aircraft or car making industry is working. Mass production. And the only SMRs could produce this opportunity. That's why, you see, so far, contribution of small modular reactors in Sustainable Development Goal is not very much appreciable. Only 2 SMRs reactors now in operation in China and reactors. But look how many designs are coming, how many countries are interested. And definitely by 2030, there are some first of a kind reactors appeared on the stage, and after operation in their countries of origin, they have a very big opportunity to be mass produced and with the contribution to the sustainable development goal significantly. So this answer, Irina.
Thank you very much for this detailed answer. Dear colleagues, you can ask questions. It will be better if you will use your microphones. You can use camera if you want and ask questions to Mr. Vladimir Artisuik.
If you please.
Professor, my pleasure.
Yes, a small question about the radioactive waste of small modular reactors in comparison with traditional or large-scale nuclear power plants. Okay, you can. Okay, you can. Because in some studies, the smaller modular reactors produce less radioactive waste than the large-scale nuclear reactors. In others, is the same, no difference. Thank you.
Yeah, thank you for very professional question. Very professional question. You see, if we compare large nuclear power plant, for example, pressurized water reactor, right, and small reactor, of course, waste will be less for smaller reactors. But if you normalize per kilowatt hour produced, it is the same. You see, it is the same. It is the same. What's important with small modular reactors? Now, several new types of the reactors are ongoing. For example, some of them with fast neutron spectrum. And fast neutron spectrum reactors, they have a neutron axis. Neutron axis, it means number of neutrons per one fission. And this neutron axis can be used for transmutation of wastes, minor actinides, or even fission products. So, for example, Russian type Brest 300, this is a fast reactor. And this reactor, along with the reprocessing facility and along with fuel producing facility in the same perimeter of nuclear power plant. So this kind of nuclear power plant consume only depleted uranium or natural uranium and as an output in form of waste. So the same radiotoxicity as excavated uranium. So because of neutron spectrum, this similar concept now under development in the United States, TerraPower. Please look at this concept, TerraPower, natrium reactor. They have a fast neutron spectrum and also oriented for minimization of waste. And in France also several concepts. So when we're talking about evolution development of small modular reactor technology. So I would say that more or less that's waste normalized per kilowatt hour electricity produced is the same, but with a new concept, which are, by the way, not just paper reactors. One of them is now under construction. So they produce less waste compared to current large nuclear power designs based on pressurized water reactor technology. That's my answer, Professor.
Thank you.
Thank you very much, dear colleagues. If you have any questions, please use your microphone. Turn on the microphone. Yeah, you can. Mr. Tamer Saleh, you can ask the question.
Good afternoon, sir.
Good
Thank you for your presentation. My name is Dr. Tamer Saleh from Telecommunication Department, Faculty of Engineering, Egyptian Russian University. Thank you for your session, but I want to ask one question about SMR. What are parameters that we should take into consideration to select the suitable SMR?
Okay. I would like to show you one slide to back up my presentation. Can you see? Okay.
Yeah.
I would like to show you this slide. Can you see this?
Yep.
Yes.
Okay. First point. Look, agency, International Atomic Energy Agency is not at the position to promote any kind of technology. I am a member of the agency, so I cannot give you just a particular advice which parameters have you taken into consideration. But what's important, look, in the agency, there is a special guidance. Pay your attention, nuclear reactor technology assessment for near-term deployment. Can you see this?
Yes.
Huh? Yes. So you can easily to find this publication on the site of the agency. And their methodology is given which kind of parameters country which is considering deployment of SMRs should consider. That is not only temperature enrichment, etc. There are several others, like stakeholder involvement, like capacity building readiness, like human resource development readiness, etc. Many parameters, not only technical one. So I strongly recommend you to look through this publication. That is rather new, by the way. Just 2 years ago, it was a revision. And though the title is just Nuclear Reactor Technology Assessment, a lot of emphasis is given to small modular reactors in the publication. That's my answer.
This will take us to the most other question about the SMR designs. If I want to consider or compare one of SMR design with the others, what is the efficient SMR design parameters to take into consideration for our country? Because if I want to govern Egyptian with SMR reactors, so I should consider places distribution of SMR units or planets, capacity of peoples or other things.
Technology readiness level also. Technology readiness level, because look, there are many designs now coming at this stage. Molten salt reactors, very interesting, very nice, very safe with the low pressure reactor. But what about technology readiness? Is there any first of a kind SMRs now under operation? So all these kind of parameters we have to take into consideration in order to show to the government which kind of decisions should be made. So I can also give you a very general answer.
Thank you, sir. Thank you.
Thank you very much. Dear colleagues, maybe a couple more questions. Yes, please, Mr. Manasek. Please use your microphone, turn on the microphone. And can
Yes, please. Am I audible?
Yeah, please. I can hear you.
Yes, so thank you, sir, for your presentation. My name is Manasek Yamlanda, part of the Russian Nuclear Education Ambassador Group. So my question is with regards to just highlight, please, some of the technological challenges that are hindering the mass production of SMRs. And also the second question is, obviously, we expect these type of reactors to take lesser time to implement as compared to the traditional reactors. but just how much less time is required. For example, when a country will plan to implement them, from like the planning to the commissioning, how fast in terms of the implementation of SMRs?
So first part of the question, challenges, right?
Yes.
So challenges, one of the very general challenges I pointed out in my presentation, it is about fuel. You see, since small modular reactors on large part they are considered for remote areas. For example, Russian type of floating nuclear power plant. It is in a very remote area of Russian Federation. Chukotka Peninsula, close to United States, close to Alaska. So there is not much population there, but there is some industry there. Remote area without grid connection to the big energy producing center. So also in Canada, also Mongolia is now, by the way, considering a small modular reactor application also for remote areas mining. So mining needs energy, so mining remote area, and what important, for that kind of option, remote areas, they mainly considered long fuel company. So real time between fuel reloading should be as long, optimized to be long. And in order to increase this fuel irradiation time, we need high level of initial enrichment. As I mentioned, 20% of uranium, so-called high level uranium, high assay, low enriched uranium. And globally, production rate of high level now is not enough to satisfy planning. That's why I have a special slide in my presentation to focus that United States of America, United Kingdom, France, they started new governmental program to encourage local national industry to produce high level, low enriched uranium. So that is the point, one of the challenges. Another challenge, also in a very general terms, we have now ready to go small modular reactors, which are evolution of the pressurized water reactor technology. But majority of other and industrial demand, they are for high temperature. And high temperature could be provided by high temperature gas-cooled reactors, molten salt reactors, but not enough experience accumulated in this domain. So we need to show technological readiness and experience of operation. This is also a challenge. If we go outside pressurized water reactor technology, we are facing the challenge. But challenges, of course, could be solved. Of course, could be, might be. Nuclear power technology has an intrinsic potential to solve all the problems. But it takes time. So time is a challenge. What about the second portion of the question? That is about advantages in terms of deployment. Am I right?
Yes, how fast and easy will they be to deploy?
No, now it's very, in fact, it is very difficult now to tell the number. You see, because first of a kind pressurized water reactor, ACP100, in China, for example, it is constructed maybe 4 or 5 years. It's comparable to large nuclear power reactor construction. So at this moment, it's difficult to tell you. But look, qualitatively, situation is clear. If mass production is able to be provided, mass production. Now we produce nuclear reactors individually. Each reactor so takes time And each reactor is like a first car producing model. Car is here and people coming to this car to install something. But if mass production, that's kind of conveyor. So of course the mass production could drastically change the nuclear power landscape. But it is not at the stage, not at the reality. It's just a potential which have to be realized, by the way, within 1 decade. And people are working on them. So mass production also invites and invoke 3D printing of some of the details for internal core of the reactor. So that's numbers here. It's difficult to tell you. Thank you.
Thank you for answering. Dear colleagues, maybe one more question, and then we will ask Mr. Artisuik to write answers in the chat. Because of timing, if you have some questions.
Yeah, sure. I have a question. Can you hear me?
Yeah, Joyce.
Yeah. Okay. Thank you so much, Sir Vladimir, for your presentation. It was like really interesting. And here my question goes to economic scale, like how attainable for these SMRs, especially in developing countries, as they are most of them newcomers in this industry. You told us about the slide of those parameters in article of 2020. I don't know if it's also 2022. Yes, yeah, I don't know if they are also included in them, and if they are, may you please kindly share with us the link to this article? Or yeah, thank you. This was my question.
I sent this link to Irina, and Irina will share with you. But look,
okay, thank you.
Economical estimation. It is very challenging endeavor. In fact, you see. Let me give you a qualitative example. Just qualitative example. For example, developing countries. For example, somewhere in Africa.
Yeah.
So usually these countries, they don't have enough installed capacity. I will give you an example of Mongolia. Total installed capacity in Mongolia, 1.7 gigawatt electrical, total, generally, in the country. Large nuclear power plant, 1 gigawatt. So if this country would like to invite large nuclear power plant, it means they have to install a new grid first. Second, this country have to be very much careful about reservation of the capacity. If, for example, nuclear power plant with so big capacity for stop for maintenance, which kind of sources should provide reservation? So you see, big nuclear power plant for small country is very challenging. That's why small reactor, 100, for example, megawatt, that's okay. So it's not a big demand and distortion of the grid capacity of the country. And of course, in terms of economics, we have also weighed two factors. First, you see, why nuclear power industry in 1950s started to go to the large capacity? That is economy of scale. So you invested in materials and produce more energy. If you invested in materials and produce less energy, so that's higher price and cost of electricity. So generally, at the very beginning, so large nuclear power plant obviously produces a lower cost for electricity. But mass production of the small modular reactors can compensate this effect. And for developing countries, step by step, first step that is installed, one reactor. After that, industrial growth in the country, new demands, they put next small reactor. Again, growth of the economy, demands growing, next reactor. So serial construction of the reactors, both beneficial for vendor country and also more suitable for developing countries with a small grid. So economics, that's too many details. I will not cover in my answer, even in one lecture.
Did we answer on your question? Did Mr. Artisuik answer on your question?
It's difficult to answer. The question was exactly,
Oh,
it's focused. What is the,
okay.
yes, but
Thank
it's
you.
impossible.
Okay, so thank you very much for your presentation, Mr. for the detailed answer on all of the questions. And dear colleagues, if you have more questions, we will ask you to write your questions in the chat. And Mr. Artisuik, if you will have this opportunity, can you please answer there? Or I can write you a message with
Yes.
this question.
And I will send you the link to the publication, Irina.
Yes.
Thank you.
Thank you very much.
Thank you.
So thank you one more time. And due to technical issues, I want to give the floor to the next speaker, my colleague from Rosatom Technical Academy, Mr. Anton Diachenko. He will tell us about very interesting and very relevant topic, the training of personnel and for facilities issues of SMR personnel training.
Good afternoon, Irina. Good afternoon, dear colleagues. Are you hear me?
Yeah, we can hear you very well.
Okay, and I should to share with my screen.
I made you co-host. I think you can do it.
Okay, you can see my presentation?
Not yet. Yes, now yes.
Okay, let me start.
Yep.
Thank you. Thank you, first of all, for the ability to participate in this event, and I'll try to share you with my short presentation or brief presentation about our academy activity in the field of personal training for SMRs reactors, and maybe a few words about the issues that nowadays we have. But first of all, I should start with the thesis that the well-trained personnel and trade in time is the main aspect to, or maybe the key aspect to safe operation of small modular reactor, and also the ability to take in the time the license for operation from the regulatory body. And this is dealing with the personnel of nuclear power plants. And first of my presentation, I have some brief slides about our academy of Rosatom Technical Academy. Our organization been established in 1967, and nowadays we prepared more than 470,000 people since 1967. And typically for industry, for Russian industry, we prepared about more than 25,000 people per year. Nowadays, until from 2022, we trained more than 1,000 personnel of nuclear power plants, or 4 nuclear power plants per year. This dealing with this fact that our academy nowadays involved in the projects for personal training of Akkuyu nuclear power plant, Bangladesh nuclear power plant. Are also nowadays we involved in the project for preparing the staff or preparing the personnel for Egypt nuclear power plant. And also in our academy we provide training courses for our foreign partners, for foreign participants, and typically per year we trained about more 1,000 of foreign participants on the short-term courses that we provide in our academy. Areas of academic activities are represented on this slide. First of all, the nuclear infrastructure personal training we also provide. We also have the special training in the field of safety of nuclear facilities. also training in the field of environmental protection, radioactive waste management and hazardous industrial waste management. But main, I think, the activity of Academy dealing with also the personal training of nuclear power plants. These slides represent information of academic resources. So nowadays we have the 5 different places in our academy where we provide the training. The headquarters in Obninsk, and 4 branches that are located in Moscow, in St. Petersburg, in Sosnovo Bor, and in Novovoronezh. And last of 2 of them, like the Sosnovo Bor and Novovoronezh, are located in the cities near the nuclear power plants with 3+ generation reactors with VWR 1200 reactor. In the field of cooperation with international organizations, nowadays Academy have the status of International Atomic Energy Collaboration Center in the field of non-power use of nuclear and radiation technologies, nuclear security, nuclear knowledge management, as safeguards, and non-proliferation. These slides represent the information and the years of when we obtained such statuses. About the information about the training in the field of SMRs, we start our activity for training of foreign participants until 2011 from the technical seminar on the topic that called the development of training programs for foreign specialists on the nuclear power plants in Russia. And then after that, we organize or provide a few special training for our international partners or our international colleagues on the topics of different types of reactor, like the lead bismuth reactor in 2013, like the water-cooled reactor, like KLT-40S, that nowadays operates on academic Lomonosov floating nuclear power plant in Pivek, and special training courses in the SMRs with high temperature gas cooled reactors. I should pay attention that we provide a few trainings of the SMRs for floating nuclear power plant, and our participants who participate in this training courses also visit the Baltic shipyard where this floating nuclear power plant being constructed, and by themselves, they saw the progress in the construction of such a floating nuclear power plant. Because, for example, in 2015, when we first time we moved for this Baltic shipyard, we saw only barge and no equipment inside that. And maybe in 2017, in the short time where we have the ability to visit the Baltic shipyard, we also there see the main control room, the equipment inside the barge, and so on and so forth. One of the next activity of our academy, they are dealing with the transfer of education. The purpose of this activity is to develop and promote nuclear education in special universities, specialized universities of our partner countries. And the key project in this area is the Train the Trainers program. And Academy with the Russian universities provides some special training courses under this project and under this program that focusing on the some of technologies, and also the provide information on training methodology aspects for the how to develop training materials, how to provide training, and so on and so forth. And in the field of small modular reactor, in until 2021, we start in this training format training for our colleagues from universities. And this year in the February, we provide a special training on SMRs. And the end of this year, maybe the beginning of 2025, we are also providing training of SMRs in the training format. If you have, if you're interested in more detailed information, please write the Irina. I think that more detailed information she provide you about this training. But as I already said, the main activity of our academy are also dealing with the train the personnel of nuclear power plants, and this slides represent the information of the concept and about the what kind of activity academy provide in this field of nuclear power plant personnel training. First of all, the creation of nuclear power personnel management system, creation of system for personnel training and nuclear power plant training center, then training of operational personnel, creation of the system for personnel training at the nuclear power plant training center, like the development and building of the personnel training system, development of training materials, and so on and so forth, and the creation of the human factor reliability system. These slides represent the information about the training system and the principles for its building. The general principle of training, we are also in our activity based on the well-known the systematic approach of training that common used in the all countries who take part in the International Atomic Energy Agency. In the publication of International Atomic Energy Agency, you can find the good description of this systematical approach of training, how to train, how to prepare the training programs, how it should be developed, and so on and so forth. In the case of new units, training is performed on the basis of proven methods. Personal training is performed in the practice methods, and so on and so forth. And the factors determine the personal training concept for the particular projects, the level of nuclear infrastructure development, the customer's country, customer's possibility to provide nuclear power plant with personnel who compliant with the qualification requirements to indication at work experience, and the availability of the similar reference unit in operation in the customer countries. The next slide, the next slide, this information about our completed projects and the current projects that we nowadays are involved nowadays in the personal training for nuclear power plants. As I already said, it's like the RUPUR nuclear power plant personnel training, AKUU nuclear power plant personnel training, LDABA, and the PAKSH-2 nuclear power plant. And the completed projects like the Bushehr, Belarus nuclear power plant, Kazan-Kolam, and Taiwan. And about the main aspects in the nuclear power plant personnel training, this slide represents information about the typical layout of NPP personnel training. And I should pay your attention that by the beginning of the power startup, all nuclear power plant personnel must be trained. This is one of the requirements from the regulatory body, and without this license, without the well-known the technology and licensed personnel, it is impossible to have the license from the regulatory body. That is in-time prepared personnel, trained in time personnel is very important for nuclear power plant. And about the layout, you can see that typically from the pre-contract phase, or maybe from the beginning of contract, before the first concrete, typically the training materials are developed, initial test of knowledge provided for the participants, and that the training on the reference nuclear power plant, the theory, technical training aims intention, and so on. On the second stage, the training on the contract nuclear power plant, also the theory, technical training aids intention. After that, licensing of the personnel, it is possible to start the physical startup and the power startup. As I mentioned in the presentation of Vladimir Artisuik, it is mentioned that the construction period of SMRs reactors is less than for the large nuclear power plant, but the amount of the information about the nuclear power plant, about their system, is really really the same for the SMRs and for the large power plant. And this is one of the issue with the staff or with the personnel, is the time or period for the training of nuclear power plant personnel. And I think that the universities and the abilities of universities to start at the beginning of stage of the future personnel of nuclear power plant is one of the important part of the training of the personnel and training for the personnel. And the next and the last slide, there's some information about our activities in the personal training for SMRs. In 2015, we start in the St. Petersburg branch of our academy, the training of the first crew of floating nuclear power plant. You can see the slide, the concept of this training. First of all, entry-level test, then development of individual training program, specific positions, theoretic training, simulation training, on-the-job training for obtaining the permit from our regulatory body, Rostechnadzor. In 2021, we start our activity for the development of a special training system or special training methodology for lead reactor Brist 300, and nowadays we on the stage of the development of training programs for the personnel. And also nowadays we beginning the start of our activity for development of training concepts, development of training, next development of training programs, and next development of training materials for the SMRs based on rhythm 200 reactors. I think that is the end of my presentation. Thank you for your attention.
So thank you very much one more time. And I want to give the floor to the next speaker who already opened our discussion, Mr. Moustafa S.El-Koliel. Please, the floor is yours.
Thank you, Mrs. Irena. My presentation under the title of Design and Performance Analysis of the Molten Salt Fast Reactor meet the requirements of the fourth generation. Small modular reactors come in a variety of types and subsystems, each having its own characteristics. For instance, light water reactors, liquid metal reactors, gas-cooled reactors, which meet the generation 4 requirements, and its output power below 300 megawatts are considered as smaller modular reactors. I select another type. It's the molten salt fast reactor. Molten salt fast reactor. Molten salt, this concept is used to describe the fuel. The reactor operation is based on the cerium fuel cycle. We have utilized it in our study two types of fuels, cerium and fissile element fluoride. It means uranium 233, or cerium and transuranic fluoride dissolved in molten salt from lithium fluoride. The molten salt also used as a coolant in our reactors. The fast reactor is a category of nuclear reactors in which the fission chain reaction is sustained by fast neutrons. Molten salt fast reactor is advanced reactor meets the objectives of generation 4 reactors, which including sustainability, safety and reliability, fuel resource optimization, waste management, proliferation resistance, high operating temperature. The high operating temperature leads to higher thermal efficiency. This means greater electricity generation from the same amount of fuel. The molten salt design allows for easier online fuel reprocessing. The reactor included 3 loops: the fuel loop, the intermediate loop, and the conversion loop. In our study, we have modeled only the fuel loop. This is the fuel salt, which is considered as a coolant also. The radial fertile blanket, which is a part of the reflector. The fertile blanket is 50 centimeters thick, filled with a fertile salt from lithium and sodium fluoride to increase the reactor breeding ratio. For neutron protection, there is a layer of boron carbide as a neutron absorber. The thick top and bottom reflectors, they are made of nickel alloy and designed to absorb more than 99% of the leaking neutrons. Fuel online processing unit, it separates the actinides, uranium, and thorium, and storing them in tanks. The fuel salt flows from bottom to top in the reactor cavity and then circulates through 16 groups of pumps and heat exchangers located around the core. The core is cylinder. The core is cylinder. Located around the core. The total volume of the fuel is 18 cubic meters. Gas injection system. This system is used to control the reactivity by injecting helium bubbles to reduce the reactor reactivity, or fissile materials, I mean uranium 233, to increase the reactivity. Gas extraction to remove the gases of the fission products. Draining system can be used to a plant shutdown or in case of emergency shutdown to prevent rapid increases of core temperatures and unacceptable reactivity. This design was innovative by the European Atomic Energy Community. It's a project named EVOL. This is the design parameters of the reactor. This is the composition of the fuel. We adjust the fissile element for K effective equal 1 by this system, the gas injection or fissile. This is the dimension of the reactor, the dimensions in millimeters. Greatest challenges of the molten salt fast reactor. The structural components is subjected to a variety of operational conditions, such as exposure to higher doses of neutrons, exposure to very high temperature, and extremely corrosive environment due to the hot salts that are chemically corrosive. The corrosion increases with the increase of temperature and velocity. The main aim of our study is to optimize the core design of the reactor to eliminate the hot spots to improve the core life span. I will show you the problem. This is two models from the literature. In nominal flow conditions, large vortex due to the turbulent flow appear near the structural core walls, which lead to excessive high temperatures, hot spots. Several studies in the literature were carried out. One of them had a fuel flow distribution system as the core inlet. To distribute the fluid flow rate according to the energy generated. The modified design eliminates the hot spots, but the fluid flow velocity was very high. In our study, similar designs were simulated and analyzed, but at the end, we propose a design capable of eliminate the hot spots and at the same time reduce the velocity as low as possible to avoid the hot spots appearance. This is the model from the literature, and this is our model. The difference between the two models, we changed the curvature of the channels from circular shape to ellipse shape. Also, we have changed the dimensions of the channels. The methodology of our study, we have used NDF library. Included 238 groups for fast resonance and thermal groups. The geometry of the reactor was modeled in the scale package software. The scale package included two programs, Origin and Triton. They were used for the neutronics and the fuel depletion calculations. Or by using the geometry of the reactor, the library, the scale package calculates the composition of the fuel and the reactivity. This is the 9 groups of the neutrons. 3 for fast, 5 for resonance, and 1 for thermal. To validate our results, we used console software, multiphysics software. In this code, we have solved 9 diffusion equation and 6 for the delayed neutrons. We have applied the finite element method, which embedded in the console multiphysics software. To validate our results, as I have mentioned, we compare the reactivity from neutronic model of console with the scale package. We have also calculated the power density, the neutron flux, and precursor concentrations. The power density and the geometry of the reactor were used in the thermal hydraulic model of console to calculate the temperature distribution and the velocity distribution, which in turn they used in the neutronic model to calculate the reactivity, the power density, the neutron flux, precursors concentration as a function of temperature. The power density and the velocity distribution used as an input to calculate the fuel burn-up. The fuel burn-up goes to the neutronic model to also calculate the reactivity, the power density, neutron flux, precursors concentration as a function of temperature and the fuel burn-up. The composition of the fuel, the library of cross sections, the geometry of the reactor were used by MCNB code to calculate the breeding ratio. This is the outline of our methodology. This is modeling of the reactor in console and scale reactor, code. We have applied 3 different number of meshes of the reactor to study the effect of mesh size on the calculated results. In model 1, we divided the reactor core to 8,665 meshes. In number 2, we utilize 25,084 meshes. In this model, we utilize 217,105 meshes. This is the velocity distribution. Near the reflector, the flow is turbulent, the appearance of vortex flow, and this cause excessive temperature and the hot spots appear. This is a distribution of the temperature which we have get from the models. Due to the symmetry of the reactor core, 1/16 only 1/16 were modeled. This is the temperature distribution. We have, it's clear here that there is no hot spot near the reflector. This is a velocity distribution. The maximum, it's very low. This is temperature distribution for another case. And this is also the velocity distribution of this case. We have also calculated the neutron flux, 9 groups. The fast neutrons, the maximum of fast neutrons, we have noticed that it's in the reactor core. But the thermal, the maximum of the thermal neutrons were in the fertile region. Thank you very much for your attention. That's all I have. Thank you.
Thank you very much for your interesting presentation.
Because you have given me 10 minutes only, so I'm...
Yeah, but it's okay. Thank you very much. But unfortunately, we have only an opportunity to ask one question because of time. And maybe if you can ask any question, but write them down in the chat, and then we will ask to answer you if it's possible. So dear colleagues, if you have questions, you can ask just one question with microphone and then write to the chat.
Oh, I have a question.
Yes, please.
So how do molten salt reactors address the issue of fuel cycle sustainability and long-term waste disposal compared to the other type of nuclear reactors?
If you please repeat your question, because the voice is not clear.
So my question is, how do molten salt reactors addresses the issue of fuel cycle sustainability and long-term waste disposal compared to the other types of nuclear reactors?
How I can model the precursor's concentration? Or
sorry, can you repeat the question, please? Mr. Moustafa S.El-Koliel, did you get the question?
I didn't understand.
Yes.
What it is. So,
sorry, can you please write your question in the chat? Or
yeah, I have written down in the chat.
you can write.
Okay, so one more question with microphone, and then I will kindly ask Mr. Moustafa S.El-Koliel to answer on your questions in the chat. Okay, as far as I can see, no more questions. So we will kindly ask to answer on all questions in the chat. So thank you very much for your interesting presentation.
Thank you very much.
Thank you. And summarizing our meeting, I would like to give the floor to one of the organizers, the leader of outreach group of ambassadors of Russian nuclear education team and graduate of the Egyptian Russian University, Mr. Khaled Ramadan. Please, the floor is yours.
Thank you. I'm visible and audible?
Yep, we can hear you.
Can I share my screen? My screen is, my presentation is visible?
Can you please press F5 and we will see the
Of course, of course.
Yeah, nice.
So thank you, Irina. So I would like to express my my glad that I am participating in such an event, not only as part of the ambassadors of Russian nuclear education, but as a graduate of the program of Egyptian Russian University and Tomsk Technical University that was just mentioned by Mr. Moustafa. So I would like to start my presentation very simply. I know that we are limited by time. I would go faster as I could. So I would like to start with the energy demands that we are looking for. It's the earlier the development of the nuclear energy. So since we are seeking for energy every day, so nuclear keeps developing every time. And specifically, when we mentioned the small modular reactor, it was there because of not just energy demands, but for different applications. So we are not only seeking for energy, but for different applications, because the nuclear power plant or large-scale nuclear power plant, they have some kind of limitations for some applications. So this is the role for this event, and describing this is what I'm going to do today. So firstly, the small modular reactor is, as many reactors, they run with the light water, or they also run with the graphite moderator, high temperature gas-cooled reactor, and the fast neutron reactors. And in order to understand how they are important, we need to see the map of the world projects of the small modular reactor. And when we see this, then we know that there are many projects that are still under construction or even constructed. So, and we can see here that Russia here have the leading with number of SMRs, comes after the United States, and of course the China. So this shows that it's really important, and we need to understand why it's important for such technology. So for the importance of the small modular reactor, we can check the advantages for the small modular reactor in order to see the features for such type of the reactors. So here on the left side, you can see that Al-Dab'a nuclear power plant that is under construction right now have the large scale, which is suitable for its application. But for other applications, we need more flexibility. So those flexibility we couldn't get from such a type of reactor. But from the small modular reactor, we can see it could be a land base and a sea base. So this sea base, just a moment. So this is sea base. So this unlock many applications, many possibility for different applications. So here I won't go much through the advantages and disadvantages. They are visible and we are limited by time. So you can read them, this presentation you will have, but I need to focus on the safety features. Here, as for me as an engineer of nuclear power plants, so safety is number one for me. So I am looking here and focusing on the safety, the advantages of small modular reactor, on the safety challenge. So here we have, we can see that the passive safety system is a bit more higher than the large scale nuclear power plant. Not only, but also due to the compact area we have here, in case of accidents, we won't have this high effect due to such a case of accident, and many others. So here we can explore the features. So due to the low compact, as just mentioned by some of our colleagues, the maintenance of the energy, I mean the capacity of the nuclear power plants in our plants, they are just low power, so we don't need to have such kind of maintenance. We also have the manufacturing, not a big issue because we are dealing with not a very large scale component. And also we can say we can see here that, as we mentioned, we have a ground based, so land based, yes, and sea based. It will have the many applications for this, as we mentioned, and also the remote regions, as we mentioned. And last but not least, the decommissioning and dismantling process, which now is one of the important technologies the countries are seeking for. So the dismantling process in such reactors are quite easier. So let's move on to the applications, and this is what we were starting our presentation with. So while you are just checking these applications, I would like to highlight three examples for such applications from three different countries. So I would like to highlight, for example, here in Russia, the application could be the district heating, as we have here the cold weather. So district heating would be an application for the small modular reactor. Moving to Egypt, that we have the example of the high dam. So let's say the support of the renewable energy is an application for this, because the high dam have just some kind of limits by area or even by the capacity. So this could act as an application for Egypt. But for example, in Saudi Arabia here, we have the distillation plants, since they have no, I guess, for example, rivers or like pure source of water. So a distillation could be a good application for such small modular reactors. And there are many other applications such as icebreaker and so on. Here you can see some of the small modular reactor projects and how they are this kind of arrangement for such shipping on this, on this ship on the sea. So here we can see the reactor. Here you can see the turbine building. You can see the waste management area, or the auxiliary building, and so on. And here we can see the information regarding this. You can see the sorry. Okay, so we can see the dimensions, length and height, and the way of such kind of projects. I would like to say that the development for such reactors started since 1975, and this keeps developing. So here we can see such examples is the nowadays developed reactors of the small modular type. And in addition, Russia and Federation has this reactor that we will be mentioning later on such active project for such type of the reactor, the RITM. And let's move on. Here, this RITM is one of the developed reactors, where we have here, you can see the reactor core. We can see here the steam generator, and here we can see the pumping. So those are the pumps for the reactors. And this, what we can see for the such type of project. So last, I would like to end my speech with saying that Russia have recently launched this type of the reactor that we just early mentioned with Uzbekistan. So Russia have the lead in such type of the reactor, and they proved it by just signing such type of the project in Uzbekistan for the small modular reactor. So this shows how these types of reactors are important, and many researches, many developments shall be done into such kind of reactor. And I encourage really to the new students, the new participant, I'm not participant, but the new postgraduates or some people who are studying into the nuclear field, to take a look through this and establish many data about the small modular reactors. So I hope this presentation was informative. Thank you very much for your attention.
Khaled, thank you very much. And I want to use my role as a moderator one more time and ask you a small question. Can you please tell us a couple of words about your project, Russian Nuclear Education Ambassadors? Just maybe several sentences. Yeah, sorry, you want to ask something? Excuse me, Mr. Moustafa S.El-Koliel, you want to ask something?
I have, if you please, I have received the 3 questions.
Yes, sure.
I will begin from the third and the second and the third. The second, why did you choose in your study molten salt fast reactor? What are the advantages and challenges of this type of reactor? The third, molten salt and the impurities within it often corrode metals, ultimately causing them to crack, weaken, and fail. How can this challenge be solved? I think this two questions are interrelated. I believe that the significant challenge of molten salt fast reactor is to find materials that can withstand the high temperature and the corrosive nature of the molten salt. This is the significant problem or a challenge of this type of reactors. It's a material problem. It's a material problem. I can share with you. Oh. The reactor is a molten salt fast reactor falls under the umbrella of small modular reactors. This means the molten salt fast reactor share the advantages of the small modular reactors, such as scalability and scalability, sustainability, proliferation resistance, waste management for resource optimization. So I have written at the end, molten salt fast reactors are a type of small modular reactors which offer potential benefits for scalability and deployment. So this is the advantages. The disadvantages is a coercion environment. And this is a material issue. The first one, okay. In our model, we have utilized two types of fuel, and the reactor operation is based on the thorium fuel cycle. We know that the thorium is more abundant than uranium and less expensive. This type of reactor burn the waste of the large-scale reactors. Here you can see thorium is mixed with uranium 233. But here in the second type, the thorium, this is fertile. Fertile means non-fissionable. Is mixed with transuranic. Transuranic, its actinides come from the spent fuel of the conventional nuclear power plants. So this type of reactor use the waste of the large reactors. This type of reactors produce fuel. After 33, this type of reactors produce fuel sufficient to operate another unit. In addition to own fuel, it can produce fuel sufficient to operate another unit. Now I can, if you have any comments, questions.
Okay, thank you very much. Thank you, Khaled. Can you please answer on my previous question? Maybe just one because of time and then one.
Yes, okay. So regarding the project that we are running of the ambassadors of nuclear education.
Sorry, Khaled, can you please turn on the camera?
Oh, sorry.
Yeah, thank you.
Invisible?
Yep.
So yes, so the project is launched by Rosatom. It is the project of ambassadors. So we are a group of people, of the students actually who are studying in Russia. Those students are just, of course, they come to Russia, they have gained some experience, and now they are supposed to share those experience with their countries. So, for example, I'm sharing my experience with the Egyptian students who are interested in studying in Russia, not just in the nuclear. I'm encouraging even them to look through the field of the nuclear energy. And if some of them are already interested, I'm giving him my experience, how it is working here, how the study is going. And we are doing this when we are just making kind of events and webinars. Some of them are online, some of them are offline. This event is typically one of them that we are running right now. So such events are just to explore our role of energy. Many of the organizers, so for example, Rosatom Technical Academy and IAEA, we also are cooperating with them. So this project is, for me as a leader for this project, I'm helping the people to just organizing some events or webinars for such kind of education in the nuclear industry in Russia.
Thank you very much, Khaled. I think you can write your contacts in the chat. It would be great. Maybe some students will touch and ask you, write the questions for you straightly. And maybe the number of participants of your project will increase. Could be a great idea. So thank you very much. I think everyone can write their contacts to ask the questions, because unfortunately we need to go on because of the timing. And maybe one more question, dear colleagues, if you have maybe just one more question, and then to any speaker. And then we can move on. Okay, no more questions. If you have them, just write them on the chat box. And thank you very much. So, dear colleagues, I would like to thank all the participants of our meeting who found the opportunity to join us today, and hope that we will be able to hold such meetings more often. So, thank you very much and goodbye.